Uh, all right, so tonight our speaker is going to be Satya Gontcho. Satya is a project scientist working at the Lawrence Berkeley National Lab. She's currently the lead observing scientist for the Dark Energy Spectroscopic Instrument, which is working to build the largest 3D map of the universe ever made by humanity. She's held postdoctoral appointments at the University of Rochester and the University of College London. Prior to this, she earned her PhD at the University of Barcelona in 2017 and her master's in science from Sorbonne University in Paris in 2013. Forbes magazine listed her on their 30 under 30 watch list in 2019. And in the same year, she received the Giuseppe Sciacca International Award for her scientific excellence and commitment to mentor future generations. So Satya, I'll leave it to you now. I think that
you should hear me. I think my slides are displaying, and hopefully this evening goes without a hitch.
Yes, I think we're good. So I'm gonna dip out for 45 minutes and I'll come back. Again, text me if there's any trouble or incidents in the meantime.
All right, thank you, Stephen.
We can test that. Satya, can you hear the audience?
I could hear that someone spoke, not what they said.
Okay. So yeah, I guess if we could save questions till the end, just because I think logistically that would be the easiest thing. If there is any really burning questions, I guess you can come up here and ask, but for most questions, if we can keep it to the end, that would probably be easiest. Okay, thanks. Go ahead, Satya.
All right. So good evening, everyone. I'm very happy to be with you tonight. And as was told, I was unexpectedly held up. So I'm glad we figured out a way to still make this happen. And I would like to thank you all for making the time to join us today. So my name is Satya Gontcho. I work up the hill at Berkeley Lab. And through this opportunity that we have to exchange with each other today, I want to tell you exactly how we know what we know about our universe and how do we go about mapping the universe, about piecing together its history, and what can going through this exercise teach us about 95% of the content of the universe, namely dark energy and dark matter, which I refer to in the title of this talk as the dark universe. And so finally, I also want to address questions that come back often when talking, to family members or members of the public about my work is, why do you need to have so many different telescopes and satellites and observing facilities dedicated to look at the night sky, at the same part of the sky? What is it that you're getting more that you didn't get before? And so that's what I want to, cover with you tonight. So as a classically trained scholar, my first instinct is always to start by paying very careful attention to the words that we use. And so I would like to start with the etymology of the word cosmology. So the first part of that word comes from the ancient Greek cosmos, meaning world or orderly arrangements. And it was believed that Pythagoras was the first person in history to use that word to refer to our universe. And then we have the word forming element logia, which means the study of, the theory of, the discourse, the understanding of. And so with cosmology, we aim to understand the world that we live in. And that means answering questions such as, what is the universe made of? What is its past history? What will its future be? And what does that mean for our future? As I mentioned earlier, I am an observational cosmologist. And that means that the starting point of my investigation is to simply look up at the sky. Now, I grew up in urban areas, and believe it or not, I never experienced a dark night sky full of stars until I was well into my 20s. I saw the Milky Way with my own eyes for the first time when I was 27 years old, somewhere in the Atacama Desert of Chile. So I understand very well that being able to look up at a dark sky is a privilege. But if you're lucky enough to look up at the sky in one of the Earth Dark Sanctuary, that is a place preserved from the proximity of human activities and their artificial lights. You have Big Sur not too far, or one of the darkest sky in California is in Lassen. That is what you may be able to see with your very own eyes, that picture. This specific picture I took at Cerro Tololo Inter-American Observatory in Chile. And it's easy to imagine how such sites can ignite curiosity and thirst for understanding the world that we live in. And so from what we know, civilizations past had an easier access to dark skies, but a different, some would say more primitive understanding of the laws of physics. Now, our civilization has made great strides in the 21st century in that regard. And so, strong of our understanding of other areas of physics, we have very diligently looked at the sky, our past, and pieced together the history of the universe. The idea being that the better we understand the evolution of the universe up until now, the better we will be able to predict what is to come. So let us start by establishing our place in the world. You can see on the left-hand side of the picture what looks like a structure on the sky. That's what's highlighted in yellow here, and it's our home galaxy. It's the Milky Way. We are sitting not in the center of it, but on the outskirts of our galaxy. And so when we're looking out into the universe, we're seeing the main trunk of our galaxy. It's called the galactic plane. And by that, I mean that think of it as if you are standing in an empty room and you're looking at the ground right beneath you. You'll see the ground, of course, but then a part of your field of view will be hidden by your torso and your legs and your feet, right? It's blind spot, if you will, that prevents you from seeing the ground that's right underneath you. But you can see it a little bit further away. And so that's kind of the same. The Milky Way, the body, because we're sitting on the outskirts of the Milky Way, part of our view of the sky is always going to be obscured by the body of the Milky Way. Now, if we change our viewpoint, keep in mind, we haven't yet mastered intergalactic travel, so we cannot get out of our galaxy. We can not even go outside of our solar system. So this isn't our galaxy that I'm showing you, but it's a galaxy that looks a lot like ours. So we live on Earth, and Earth is part of a collection of planets orbiting around a star called the Sun. That's the solar system, and it's organized around one single star. Our own galaxy holds 100,000 million stars. And our galaxy is only one of the many billions of galaxies in the universe. It's not even a particularly big galaxy. So everything we know it from the point of view of standing here, living here on Earth, in our tiny little corner of the universe. And this corner of the universe is where we developed our understanding of the laws of physics. And that brings us to a very important postulate that is essential for everything else that I'm going to tell you today. We, as the scientific community, we assume that the laws of physics are the same everywhere in the universe, and that there is absolutely nothing special about our place in the universe. And so anything that we understand here, that works here in our corner of the universe, that's also going to be applicable anywhere else in the universe. And so, by the way, this picture, as well as the first really nice presenting galaxy that was on my title slide, I took them in 2018 with DECAM, the Dark Energy Camera, the most powerful optical camera in the world. Think of your iPhone, but only so much better. So DECAM is hosted on the Blanco telescope in Cerro Tololo, Chile. Now, if we can photograph this with Dicam, what else can we photograph with the most powerful optical camera in the world? Well, this. If you look up at the sky and you take a picture with a really good camera, it may look something like that, actually exactly like that. This is a very teeny tiny piece of a 5 years effort that I took part in to take pictures of 1/3 of the sky, the largest imaging map in existence, so yes. What you're seeing, it's actual real astronomical data. And the previous pictures I've shown you are hidden somewhere in there. Only what you're looking at right now, it's just a very, very zoomed out version or, area. It is called the Dark Energy Spectroscopic Instrument Legacy Surveys, that collection of images. And all of our work is public, and it's accessible by anyone at the URL at the bottom left. So you can just go to that URL and start clicking around and navigating inside this picture, zoom in on objects, learn more about them. Now, my question to you is, how do we go from such a simple picture, right? So a 2-dimensional image, from being able to construct a 3-dimensional map of the visible universe? And how does building that map help us understand what happened in the universe several billion years ago? Well, one of the greatest difficulty and accomplishment of astronomy, which is in essence the cornerstone of our field, is our ability to correctly measure distances of galaxies and other astronomical objects that we observe. So understanding how far away something is from us. Now, let's understand how accurately measuring the distance in the universe is our key to understanding its past, its fate, and the nature of what makes up the universe. So if you look at this image, say we can identify which galaxies are closest to us, and then which galaxies are a little bit further away from us, and then either, further away and even further away. Now, just as a detective would be putting the clues collected in the right order and using perspective to extract information from its clues, we are able to use a 2-dimensional image of the sky to divide it into different slices of different depth and to create a 3D reconstruction of that specific part of the sky. You have heard that nothing can travel faster than light, and it is true. Light travels very fast, but all the same, the speed of light is finite. And what that means is that by the time light from distant galaxies has traveled all the way to us, and we read the information carried by that light, that information is already outdated. And so the deeper we look, the younger the universe we're looking at. And so if you do that with many, many images pointing at different parts of the sky, then the larger the 3D reconstruction you can do. And the deeper we can see, the further back in time we can go and access information. So this 3D reconstruction contains information about the way our universe is ordered, its structure, but also its timeline, the chronology of how things to be the way they are. So I want to take a second now, and another way to visualize what I just told you is to imagine that right now you're sitting in the spot middle of a forest. All the trees that are closest to you are those magnificent thousands of years old trees. And then as you look deeper and further away from you in all directions, past those first trees, the trees are getting increasingly younger. They're maybe only a couple of hundreds of years old. And then if you look even further away, they're tens of years old. until finally, in between all of the trunks, at the edge of the forest, you're starting to see that these are only sprouts. So it's the same thing. We're sitting here looking at the sky, and the deeper we look, the younger the universe. So keep that mental image with you, and let's look once more at real data. So over the past 20 years, the Sloan Digital Sky Survey has achieved a tremendous endeavor of producing what was at the time the largest 3D map of the visible universe ever created. So you'll notice that I have used, and I will keep using, a lot of superlatives like the largest ever created, the deepest. It's not because I'm very enthusiastic about what I'm telling you, though I am. It's because since the end of the last century, the rate of breakthrough and progresses in the field of cosmology is simply mind-blowing. So we push boundaries, and we keep on pushing boundaries every single day. So let me play for you a video that shows the rendition of SDSS's results. And by that, I mean, we're looking at real images of the real sky. And you're going to see here in how we can move in our universe. So we start from our star, the sun, placed on the outskirts of the Milky Way, our galaxy. Milky Way, only one of many billions of galaxies. And as we travel out and zoom out in that map, you can notice that galaxies are not equally distributed. It's not homogeneous. There's a lot of empty space between them. They tend to cluster together and follow what looks like a fairly random pattern. Can you notice that a little bit? So the center of the reconstructed map, where it looks like a bottleneck or a node, it's us. It's us looking outward to the universe. And the large dark patches that create that bottleneck, it's actually regions that are obscured by the Milky Way, just like our legs were in the way when we're trying to look at the ground. That's the reason. And so this dark patch of the sky could not be observed from Earth. And this 3D map shows the results of 4 exploratory phases of the Sloan Digital Sky Survey. It was created by focusing on different classes of galaxies. So you have the nearby ones, red galaxies, then galaxies more distant that are star forming, that are called ELGs. And then you have super luminous distant active galaxies called quasars. And this 3-dimensional map is composed of 1 million galaxies. And we have used it to trace the large scale structure of the universe. So the large scale organization of matter up to a fraction of its horizon, represented here by the cosmic microwave background, this background of blue to red pattern that's projected onto a sphere. So the cosmic microwave background is the thermal relic of the universe, which dates back to 4,000 million years after the birth of the universe, also known as the Big Bang. So the very first light that can be seen in the universe, and everything before then looks dark to us. So if you followed everything up until here, you'll notice that I've been focused, and that may be completely obvious, but I've been focusing on looking at what our eyes or detectors can see, on looking at what emits light, right? We're looking at things. But as it turns out, this only represents 5% of the content of our universe. So what about the remaining 95% of the universe? Well, it's called dark energy and dark matter. And once again, I'm going to pause here, and I would like to draw your attention to the words that we use. So make no mistake, the use of the word dark is less reflective of what dark energy and dark matter are than it is revealing of our understanding of their nature. right? Because if you look at Western Europe, the Dark Ages are used to refer to an era of history where the lack of pursuit of knowledge was notable. And so we know dark energy and dark matter by their effect on other visible things in the visible universe, but we do not know their nature. And because of our lack of understanding, because of our lack of insight into their nature, we refer to them as dark energy and dark matter. And so this cartoon represents a chronology of the different epochs of the history of our universe. Moments after the Big Bang, the universe had expanded enough that light started to travel freely, and it gave us the first image of the universe, the cosmic microwave background mentioned earlier. And as the universe kept expanding, going from left to right on the image here, the first stars form, then the first galaxies, and then larger structures made of millions of galaxies are formed. However, these structures are not formed at random. The backbone that informs how galaxies will be distributed is dark matter. Dark matter is, in a sense, the invisible skeleton behind the visible universe. That skeleton is also often referred to as the cosmic web. What started as quantum fluctuations right after the Big Bang grew to shape these massive substructure with an incredible gravitational pull. So with dark matter being the heaviest type of matter, that means that all the atomic matter is attracted to dark matter through gravity. The same way that we are attracted to Earth and are staying in its neighborhood at all time, regular matter tends to fall and settle where dark matter is. And that leads us to another key point of cosmology. We use that we can see to understand that we cannot see. We use the positions of galaxies that are, in essence, light emitting units as clues of where dark matter is. Now, from extensively looking at the maps we created, we have come to know about a primordial pattern that can repeatedly be found in the way dark matter is distributed, and therefore in the way atomic matter is distributed. This pattern is called the Barrian acoustic oscillation, and it can be found at every stage of the history of the universe. That's the circular pattern that you can see over here. But due to the fact that the universe is expanding, we notice that this pattern has different sizes at different moments in time. The BAO pattern is used as a standard ruler. That means as a reference of size against which we can compare other things. Now, we see that this primordial pattern, this standard ruler, is just blown up following the fact that the universe is expanding. Just like drawing a cartoon on a balloon, blowing up in the balloon, and then you see that cartoon becoming bigger and bigger. So not only is the universe expanding, in recent times, its expansion isn't even slowed down by gravity, right? Gravity pulls things together. But no, on the contrary, the expansion of the universe is accelerating. Things are pulled apart from each other faster and faster. Now, maybe you remember this from high school physics, but where there is acceleration, you need a force to be responsible for this acceleration. And that's where dark energy comes in. Dark energy is the force responsible for that. So there you have it. Our universe is filled of atomic matter, all the matter we are made of that makes the stars and the galaxies, are of dark matter. That's the backbone of our universe and basically tells regular matter where to stand. And dark energy, that is the force responsible for counteracting gravity at very large scale and pushing the large structure made of atomic matter and dark matter further apart from one another. The proportion of those three components vary through time. And at the moment, it is as follows. So about 5% of ordinary matter, 27% of dark matter, and 68% of dark energy. So over the course of time, these proportions, though, they have not stayed the same. So shortly after the Big Bang, radiation was the dominating species at play in the universe. And that means that at the time of the universe was mainly filled with photons, neutrinos. And then came the matter-dominated era. And that means an era dominated by gravity, a force that pulls things together. And therefore, while the universe was still expanding, this expansion was slowed down by the pull of gravity. And finally, we right now very recently entered the era that is called an era of accelerated expansion. And we first realized it was the case at the end of the 1990s. It was unexpected and an exciting discovery that resulted in the Nobel Prize of 2011. One of the co-recipient of that Nobel Prize is Sol Perlmutter at Berkeley Lab. So at the beginning of the 2010s, we had in essence 3 pictures, right? We take pictures. So we had in yellow a picture in the of the first light. This cosmic microwave background, then one towards the end of the matter-dominated era, and another one at the dark energy-dominated era. 3 pictures. So how exactly does that help us understand anything about anything? And especially about the nature of what dark energy is? Well, theorists will come up with different hypotheses of what dark energy is. And these different theories of dark energy will predict different ways the expansion of the universe can go. And that means that, say you're working with theory 1, and it says, well, that circular pattern that we discussed before, this baryonic acoustic oscillation, it will be stretched differently at different moments in time. And I am telling you that, oops. Okay, sorry, let me stop sharing this and go back. I don't know why it didn't work. There you go. Yeah. And so it's gonna, make theory 1 is gonna say this baryonic acoustic oscillation pattern will be stretched at different ways at different moments in time. And this is my prediction for the sizes at different moments. And then another theory will say, well, I see something similar, but slightly different. And same for a third theory. And so the biggest difference between all of the predictions happen later in the late universe, which is when dark energy became the dominant force. So if you want to understand what dark energy is, you want to have a really good understanding of how the size of that circular pattern changed in the late universe, right? So now if we measure the size of that pattern at different moment in time, meaning on those 3 pictures that we have, we are able to compare those real life measurements to the predictions given to us by theories. So we're gonna take a step back on everything that we've covered so far. And I would love to use the word archaeologists here, but in our case, we let the evidence come to us. So we'll go with the word detectives. Let's say that we are the dark universe detectives, and our goal is to understand our universe, its history, and its dark components. We started our investigation by putting together our first and most powerful clue. That's a 3-dimensional map of the visible universe. So we use 2D images and our know-how of measuring distances to create a 3D map of the universe, right? By doing so, we also recreated a timeline of the evolution of the universe from right now all the way to when the universe was young. the primordial pattern of dark matter is imprinted in the matter that we can see, namely in the way galaxies are distributed at very large scale. We can measure the size of this pattern at different depth in the map, and which means that if we measure the size of this pattern at different epoch of the expanding history of the universe, by looking at how much that pattern has been stretched at different moment in time, and comparing that to predictions of what dark energy is, we can rule out certain theories of dark energy and keep others for further investigations. That's the beauty of the scientific process. It is self-correcting. And so we've displayed great ingenuity in applying our detective skills, putting clues together, and extracting information from such clues. So then you may ask me, how come we don't already know what dark energy is? Well, a lot comes down to our level of technology. We have those three pictures. And now, to highlight how our level of technology influences the quality of the map we built, let me simplify a little bit and give you a simplified walkthrough of the past 30 years. Now, I'm not going to use real astronomical data for this, but instead I will use images of one of my arts projects. The good news is the principle is the same and the images are kind of pretty. And that will allow me to fully illustrate my point. So you recognize at the bottom, the timeline. On your left, you have a universe that is very young. And as you move towards the right, the universe gets older and older. So let's start with 1992 and the satellite called the Cosmic Background Explorer, COBE, that was sent to take pictures of the very first light, that yellow line here, of our universe, the cosmic microwave background. The technology at the time allowed for such a groundbreaking exploration, but we were limited to very pixelized picture, not very many details. And during that same decade, you had several ground-based observatory, telescopes that measured the distance of galaxies in various parts of the sky, but the effort wasn't coordinated. And so all pulled together, our picture of the sky when the universe went from matter-dominated era to dark energy-dominated era was something that you can see here. Patchy, a little bit higher quality, but okay. Now, moving on to 2003 with the Wilkinson Microwave Anisotropy Probe, WMAP, another satellite that was the state of the art at the time of what we knew. We got a slightly better image of the CMB, as you can see here. You could see a little less pixelized. And starting the year 2000s, there was also a ground-based effort to start systematically measuring the positions of galaxies over the sky. However, our technology didn't allow us to see very deep, and we could only see the brightest and the closest galaxies, which is why we're having a picture of the universe when it's already pretty old. And we measure the position, measuring the position of those galaxies took time. Think 19th century, when you had to sit very still for several seconds so that a photographer in a three-piece suit could take your portrait. So since measuring the distance of galaxies was so time-consuming, you could do that for very little number of galaxies. And so overall, the image is blurry, and blurry in the sense doesn't have a lot of resolution and has the limitation of having a part of the sky obscured by the galactic plane of the Milky Way. Nevertheless, you can see it's still a tremendous improvement compared to what we had in the 1990s. Now, in the years 2010, the Planck satellite, an upgraded version of WMAP, gave us an incredibly high quality image of what the universe looked like at first light. And then in addition, you also had now the later phases of the Sloan Digital Sky Survey that allowed us to look at galaxies that appeared fainter to us. And if they appear fainter, that's mainly because they are a lot further away from us than other galaxies. And so we're able to have not one, but this time 2 pictures of the late universe at different depth. Now, you may also have noticed that compared to previous phases, the images are slightly bigger. Now, the reason is because technological advancement allow us to measure the positions of galaxies faster. So we can measure the positions of more galaxies. And so, if in a couple hours before you were able to look at 10 galaxies, now in a couple hours, you were able to look at 1,000 galaxies. And so you can look at more of the sky. And so the shaded hourglass area is still our own galaxy being in our own way. Finally, what we have started to do this decade, and I am immensely proud to be part of this project, is that we use the dark energy spectroscopic instrument, DESI, to measure the position of not 1,000 galaxies every 2 hours, but instead 5,000 galaxies every 20 minutes. And on top of that, we can look at galaxies that are even further away from us than before. And so that will give us, using that same example here, a depth of 4 images instead of 2. So we are also taking images of an even bigger part of the sky than with SDSS. I'm unsure if you see where I'm going with this, but let's summarize. Technological advancement for the past 30 years have brought the 90s, the 2000s, the 2010s, and right now, the 2020s. So now you're starting to realize that what we have been looking at all this time is a dancer having fun at sunset. From the few images that we've collected over the years, you see that we're able to make a GIF, a little videos of increasing quality. So now I ask you, what if we were technologically able to look a lot deeper without any restrictions and take many more high quality pictures? What would we get? Let me see if I can hear some suggestions. Any idea? Well, we would get a very high quality movie. That high quality video now allows us to see the precise trajectory of the dancer and see that at the beginning, she covers a lot of ground really quickly, and then her movements grow more subtle and she stills herself. And what's very neat is we went from a collection of images to a nice video. Now, imagine what that means for our comprehension of the universe. By consistently improving on the quality of the images that we can take, on the number of galaxies that we can measure, we become increasingly capable of recreating a movie of literally looking at what happened in the universe. And ultimately, we want to be able to see with our own eyes real images of each stage of the expansion history of our universe. And that will allow us to narrow down on an explanation of what dark energy is. And we will be able to refine our predictions of what will happen to our universe. Now that I've given you an overview of what the field of observational cosmology is about, I want to use the remainder of my time to tell you a little bit more about a very exciting project that I'm a part of at the moment. It's called the Dark Energy Spectroscopic Instrument, DESI for short, And we've worked hard on producing this little 2-minute video. So I'll show that explanation.
The universe is expanding, faster and faster, widening the nearly empty space between galaxies. We know this is happening, but we don't know why. Scientists use the term dark energy to describe this accelerating expansion. It could be caused by a previously unknown force, or we may need to rethink the laws of gravity. Dark energy is a very big mystery, making up about 68% of the universe. To solve this mystery, scientists need better measurements of this expansion rate and how it has changed. DESI, the Dark Energy Spectroscopic Instrument, installed on the Male Telescope at Kitt Peak National Observatory near Tucson, Arizona, will map 35 million galaxies in 3D by measuring their light. The range of colors or spectrum of their light will allow us to better gauge their distance and measure the rate at which they are moving away from us. This will give us new clues about dark energy. Light first reflects off of the telescope's 15-ton primary mirror, then onto its 6 large lenses that ensure DESI maintains a wide, highly focused view of the sky, covering an area about 38 times larger than the full moon. These lenses are housed in a device that can be adjusted within millionths of a meter to preserve the alignment of those lenses. After passing through the set of lenses, the galaxy's light reaches fiber optic cables in DESI's focal plane at the top end of the telescope. 5,000 robotic positioners, each carrying a single optical fiber, are programmed to move to pre-selected sequences of galaxy targets. This automated dance of robots allows DESI to target sequences of thousands of galaxies at a time. The optical fibers, which serve as DESI's eyes, send the galaxy's light down the length of the telescope to 10 spectrographs. The spectrographs separate the light from each galaxy into a spectrum of colors. These spectra allow us to gauge the galaxy's distances from Earth. Objects that are moving away appear redder because their light gets stretched to longer wavelengths. This is called redshift. DESI's spectrographs are designed to precisely measure this redshift to pinpoint a galaxy's distance and how quickly it is moving away. Taking these measurements for millions of galaxies will provide a powerful 3D map. The map will tell us which dark energy explanations fit best and whether we need to rethink our understanding of the laws of nature. DESI will function like a time machine, allowing us to see the light of distant objects up to 12 billion years into the past. This new window into the universe could help unravel the mysteries of dark energy while teaching us more about the life cycle of galaxies and the cosmic web that connects them.
And so that last statement, it hits a very important point, is that ground-based observatories are very often located in privileged places on Earth. They're considered sacred to the people that have a long history of inhabiting and taking care of those places. And that's one of the reasons that photos are not allowed, and that what I can show you are mainly, close-ups of the instruments and pictures from the inside of the telescope. And so I've mentioned that we spent 5 years collecting images of 1/3 of the sky, and that's called imaging. Then we identify the galaxies that we want to follow up on. And so indeed, we can measure the distance from simple images, but there's a method that is at least 10 times more precise called spectroscopy. And so the downside is, if you take a picture, you point and shoot, and then you just see where things are. However, for spectroscopy, you need to know very, very well ahead of time where you want to point your spectrograph, because we cannot see directly the light that we collect. It doesn't look like an image. It actually looks like what you're seeing on the screen, and the light that we collect is actually counting how many photons of which wavelength, of which color, is coming from a given galaxy. That's a spectrum. And this actually, believe it or not, makes it very easy to know what's in the galaxy, and therefore how far away that galaxy is from us. Now, I just want to show you a few cool pictures of the instrument that has already produced, as of not so long ago, the largest 3D map of the observable universe ever made by humanity. And we're only 1 year into a 5-year program. So there's a lot more exciting results to come. So we started our official program in May 2021. We shut down in July and August last year because of its monsoon season in Tucson. So we didn't observe. We did some maintenance on instruments. And so what you're seeing here is the Mail telescope near Tucson, Arizona at Kipik National Observatory. That's where we installed DESI. On the left, then you get a picture of me, a rather small human being in University in London, next to one of the barrel of lenses that were later assembled into this huge barrel that you see on the right, next to a taller human being. So that gives you kind of a size reference of how big this instrument is. And then if you plug this barrel into regular camera in order to test that all the lenses are properly aligned and that we're in focus, you can see the quality of the images that we get. This is the Ring Nebula on the left, and then the Whirlpool Galaxy on the right. And it's pretty neat resolution. And that was literally plug in, play, look at those two fields, and this is what we get. And then once we knew that we can properly guide the light, we replaced the normal camera by a sophisticated series of optical cables placed atop of little robotic heads called positioners. That's what was seen here. So the picture shows the fiber end of the 5,000 robotic positioners, and we have a mechanism to back illuminate them in blue. That's what you're seeing on the right, because we want to see where all those little robot heads are placed. For example, if you take that apart, this was me last summer when I was doing some doing some maintenance on the instrument and switching electronic card boards. And then, as mentioned in the video, we have 10 spectrographs that collect the light from those fiber optic cables and then count photons for each of the galaxies. You know, each of the little robot goes to a galaxy. So we have 5,000 of them. And then they bring up the light to the spectrographs. Each spectrograph for each of the galaxy will say, well, there is that many photons of that many colors. And that means that the galaxy is however many years, however distance from us. So that's our instrument. Then, in the telescope, you have people, my colleagues and I will decide what we observe in what we're going to be observing at night. And that's a picture of the very first night that we observed with DESI. We look a little bit stressed because we hadn't turned it on yet. And then, a couple hours later, we're a lot more relaxed. Everything worked. And what we're getting, the raw data, the raw spectra. I'm giving you here a choice example of 10 spectra. And each one of them is either a galaxy or a quasar. And I've put the correspondence between a spectra and then the distance in billions of years. So, the upper one is the oldest because, like I mentioned, it's not a galaxy, it's a quasar. And it's sending us information from a little more than 10.5 billion years ago. Galaxy underneath is, 6 billion years old, and the list goes on. And up until DESI was online, we could have that information for 1,000 galaxies simultaneously. And then we needed to wait a couple hours And then we could get that information for another thousands of galaxies. Now we can do that a lot faster. We can get that for 5,000 galaxies every 20 minutes. And the reason for that, and I love showing that example, is, this is a sped up video, but you see someone plugging in manually optical cables into a metal plate. That metal plate was designed to match only one part of the sky. And so you had to, physically plug in, look at the sky, unplug, take another plate, look at a different part of the sky, plug in, etc. And so we've replaced that wonderful time-consuming mechanism by now movements from robots, and this is in real time. And so in less than a couple minutes, we can just have them dance and reconfigure and match one part of the sky. And then we observe for 20 minutes, and then we have 5,000 galaxies in a bag, and then we move on to another place. And so more galaxies says we're making a bigger map, and the instrument is also better, and our distance measurement is also more precise. And, bigger, more precise map says better video to see how our universe has evolved. And so this is not even the most recent data that we have, but it's just to give you an idea. This is a 20-degree sweep very, very early on in our collection of data. And so the 0 on the x-axis means this is where we're standing. And this is just like we're looking, we're covering the sky bit by bit. And so as you're going deeper, or like at more distance, you're going deeper in the sky, and you see each little shimmer of white or red is a galaxy. And then you're switching to like different areas of the sky. And so you see there's kind of a motive, a pattern. Another way to look at this, this is a fly through of, these are mock points, but the positions, all of this is real positions that we've looked at, real quasars, real galaxies, and we're flying through from right now to 11 billion years ago. So that's what we're doing. And this is on a very small part of the sky, but we're going to do that for 1/3 of the sky. Finally, here's an example of one of the nights where I was observing in Arizona with some colleagues on, you have on the left, Amy, she's an American telescope operator. And then on the right, you have Antonella. She's actually also in the astronomy department here and at the lab, and she's an Italian scientist. And so another treasure of going to observe in person is the people you meet. And finally, I would like to quote a colleague of mine at Berkeley Lab, David Schlegel. He's one of the scientific lead on DESI, and he was one of the key players on SDSS for the past 20 years. And he said before starting DESI, for the past 13 years, we've had a simple model of how dark energy works. But the truth is, we only have a little bit of data, and we're just beginning to explore the times when dark energy turned on. And if there are surprises lurking out there, we, DESI, we expect to find them. But if there is something that I really want to point out, is that it's a collective effort on the part of many, many different people and many different entities. And, science requires collaboration, and we go further by working together. So thank you very much for your attention, and I'll take questions now.